Hello everybody. In today's video, we are going to discuss about directed acyclic graph and how this construct can be useful in optimization of your machine code and also in many other areas. So, directed acyclic graph or DAG as we call it, okay, DAG. So this DAG, it is a graph, okay, and it is acyclic. Acyclic means it does not have any cycles, and it is the directed graph. And the requirement and why it is used, its main task is to analyze our basic blocks. So we can analyze the statements inside the basic block, okay, which values are created, which values are used, okay, and so on. And it gives us an idea about how the values are computed and when and how, where and how these values are used. Okay, so when I say used and computed, so when I say x is equal to y plus z, here the value of x is created and the values y and z are used. Okay, so that is what we mean. So your DAG has got several uses. Some of these uses are determining common sub-expressions. Like suppose if I say A is B plus C into D, okay, and then somewhere else I have Y is X plus C into D. Okay, so here C into D, this is a common sub-expression. So in an optimized code, this should not appear twice, provided, of course, in between this statement and this statement, the values of C and D do not change. So you can use a directed acyclic graph to detect these common sub-expressions. Then we have another use is to determine which names are used inside the block but evaluated outside. Okay, like here, if say this appears in one block, then I can say that the value of y and z are used inside this block, whereas the value of x is computed inside this block. Okay, so determines which names in a block have their value used outside the block. So here x is created here, but it is not used inside this block. So maybe it is used in some block which comes after it. Okay, so all these information you can get it from a directed acyclic graph. Now let us see how we can construct a directed acyclic graph. Okay, so we will consider instructions of this type, three address instructions of this type. X is equal to y op z, where op is an operator, or it can be a unary operator statement, x is equal to op y, or it can just be an assignment statement like this. X is assigned y, x is assigned y. So our three address instructions can be any of this type. So how do we do this? We will first see, let us take x is assigned y op z. Okay, so what we will do is we'll see if y exists. If y exists in the acyclic graph, in the DAG. If it does not, then we will create a node for y. Then we will check if z exists. If z does not exist, we will create a node for z. Okay, and then we'll check if there is a node for op, okay, with y as the left child and z as the right child. If it exists, we will see what happens. If it does not exist, then we will create one with y as the left child and z as the right child. Now, if this already exists, then what we will do, and then we have to, before we go to that, here you see x is also there. We have to assign this to x. So what we will do, we will label this as x. So the value of y and z are used here, and then we have created a node for x. Okay, so we have labeled this as x. So the value of x is created out here. All right. If it is of this format, x is equal to OPY. Okay, then again, same way, if y is exist, we will create y. If does not exist, then we'll create y. Similarly, if op exists, then we will, with y as a child node, as a single child node, then we will use that op. Otherwise, we will create a new one like this, and x will be assigned here. And then for the statement like this, X is assigned Y, what we will do, if Y does not exist, we will create Y, and then X is assigned Y, so we will label this node as X. Okay, so this is how we will create the graph. Okay, so let me, this is the full algorithm for this. Okay, you can take a screenshot and then you can check this out. It's the same thing which I have explained, but it is written in a more elaborate way. So let us see this with an example. Okay, so here I have some tree address codes, and I would like to create a directed acyclic graph for it. So you can see here, I have first statement, I have S1 is equal to 4 into I. So 4, I will create, it is the first node, so I will create it here. Then I is also not there, so I'll create it 1. But here you see, I have put the node as I0 because this is the starting value of I. Okay. Now there is there, then we'll look at op is star. So is there any node with star as the parent and 4 and I0 as the leaf nodes? No, it does not. So we will create this, and we will create this tree. Okay, directed. Okay, remember this is directed. Okay, and S1, it is assigned to S1, so we will label this node as S1. Okay. Next statement is address of A minus 4. So address of A is not there. This is the first operand. 4 is already there. Okay, 4 is already here. So we will create this minus this, and we will label it as, it is assigned to S2. So we will label this as S2. Next, I have S2, S1. So S2, S1. So S2 is here. I will not create it again. S2 is already here. S1 is already here. What is the operator? Operator is indexing operator. So I have this node created, and then I will label it as S3. I'll label this node as S3. Then next is, you can see statement number 4 is 4 into I. So 4 into I we have already computed, and in between these statements 1 and 4, the value of I has not changed. So we will, it is already computed. It is here. It is here, this one here. So the same node, we will label it with S4. Okay, we will not do the computation again. We will not create new nodes again. We will label it here. So what you can see here is that this common sub expression 4 into I, 4 into I, okay, we don't have to compute it again. So we have already got it. So if a node has more than one label, it means that you have found out some common sub expression. Then next, statement number 5, address of B minus 4. So address of B is here, 4 is here. So minus, okay, and we will label this as S5. S5. Then next is S5, S4. So S5 and S4 is this one. And indexing operator is here. Okay, so what we will do, we will label this as S6. This is S6. Then I have S7 is S3, S6. So S3 is here, S6 is here, star is here. And what is this being stored in? It is being stored in S7. So S7, this will be labeled as S7. Then I have product plus S7. So product I have not created before. So product will be created. S7 is this one. So product into plus S7. So plus is this node. We'll call it S8 because this is stored in S8. Okay. In statement number 9, you see S8 is assigned to product. So we will not compute again. So we will just write product at this label, at the label which is already has a S8. Then I have S9 is I plus 1. It's not equal, it's assigned. Okay. I plus 1. So I is already, I0 is here. 1, we will create one node for this, and plus I plus 1. So what is I plus 1? It is S9. So we have S9 out here. Then in the next statement 11, S9 is assigned to I. So I. All right. So now the value of I has changed. Then I have next statement number 12 is an if. So if I is less than or equal to 20, so I is here now. Now this node indicates I, no longer I0 because the value of I has changed, and 20 is here. So this node and this node operator is less than equal to. So what do we have to do? We have to go to 1. So this is your directed acyclic graph for this code. Okay. So using this directed acyclic graph, there can be several applications, as I have already mentioned. That is automatic detection of your common sub-expressions, as we have seen out here. This 4 into I already we have seen. Okay. Then determines which identifiers have the value used in the block, which are being used. Those identifiers are used, the ones for which a leaf node is created. For which a leaf node is created. Wherever we create a leaf node, that is the use. So here product, this is used in this block. Address of A, address of B, I0, all these are being used in this block. These are the used names which are used. Then determines which statements create values which can be used outside the block. Okay, which statement creates values that can be used outside the block. So the statement S, whose node N is constructed or found in step 2, okay, and whose still has the node A N at the end of the DAG, okay. So where A is the identifier assigned by the statement S. So wherever we are creating something, like here you can see, here S9I, the values are a value for S9 and I are created. So if you're talking only about identifiers, then S1, S2, S3, these are not proper identifiers. These are temporary variables, but our identifiers are I and product. So you can see product has been created here. Then I has been created here. So all these are values which has been created and which can be used outside the block. So this information we get from a directed acyclic graph. So when we study about code generation, you'll see that this directed acyclic graph can be very helpful in performing, determining like which registers, how many registers to be used, okay, whether we can reuse the registers or not. Okay, so that is for another discussion. So that's all for this video.